Welcome to lecture 5.1 on areas and distances. We're now going to kind of shift to the second area of calculus, but that'll come in the next section. But this is kind of our link to that section. Okay? The area under a curve. It may not seem readily apparent, but calculating the area under a function or under a curve provides interesting information about that function. Here you can see a graph of f of x over the interval from x equals a to x equals b. In this diagram, the area is the shaded area S, the blue area under the function, which we don't really have an easy way to calculate the area, mainly because the function is a curve. You know, if the function instead of a curve was made of straight lines, this would be a little bit easier because we actually have formulas for areas of polygons. For example, if the function was just a constant, then we'd have one big rectangle S, and then we could easily calculate the height of the rectangle times the width of the rectangle, b minus a, and calculate the area if it was a triangle, etc. So we have formulas for polygons, but we don't have them for a curve. Remember that with the slopes of tangents, we figured out how to do this because we knew the slope between 2 points, which was the slope of a secant, and then used the limit as that secant as those 2 points became closer and closer together. And so we're going to do something a little bit similar here. Okay, so let's look at an example, and hopefully this will make it more clear. Example 1, use rectangles to estimate the area under the parabola y equals x squared in the interval 0 to 1. So here we can see we have the function y equals x squared from 0 to 1, and it tells us, or it gives us, if we divide the interval into 4 equal sections, 1, 2, 3, 4. Now again, the interval is from 0 to 1, so if we want 4 sections, we're going to divide that the length of it, or the interval, which is only 1, divided by 4, and then each section will be 1/4. So this x will be 1/4, plus another 1/4 gives me 1/2, plus another 1/4 gives me 3/4. So all I've done is divide the x interval into 4 sections, because we're going to do 4 rectangles. And if we make each section into rectangles, using the right edge values for the height of the rectangle, we get this shaded figure. Now listen, this is key, and it can be a little confusing at first. We're using the right edge values. So for the interval here, this first interval, we want to use what's on the right side. Wherever that function is, that's where we're going to make the height of the rectangle. So notice here, between 0 and 1/4, 1/4 is on the right. We're going to go to the function curve wherever that value is, that f of x value at 1/4, and then we'll draw a straight line. For the second rectangle, we're going to use the right end value, because this rectangle goes from 1/4 to 1/2, so we're going to use wherever the curve touches 1/2, x equals 1/2, and make that the height. Again, the third rectangle, the right edge value is 3/4. We're going to go up to the curve to where that touches 3/4 and make that the height of the rectangle. And then for the last one, between 3/4 and 1, 1 is the right edge value, so we go up to where the curve meets 1, x value of 1, and make that the height. Okay? So now we have rectangles that are really easy to calculate. Where'd my arrow go? Sorry, there we go. So the width of each rectangle is 1/4, because they're all the same, right? We divided this area into, or this length into 4 sections. The height of each rectangle is easy to find, because if we know x, we just plug it into the function, because y equals x squared. So for the height of this first rectangle, it's going to be the y value, or the height, is going to be 1/4 squared. The height of the second rectangle, since we used x equals 1/2, will be 1/2 squared. And so here you see the formula here. Width times height, y value, plus second rectangle, width times height, second y value, or x value squared. Third rectangle, x value squared, because that's the formula, x squared, and the last one, x squared. Okay, we do this with our calculator or whatever, and we get this value for the right edge. Notice this is an overestimate. Now how do I know it's an overestimate? I can easily see that it's an overestimate just by looking at it. Here's the area we're trying to calculate under the curve, and we can see that all of our rectangles go over the curve. Okay? Now this is mainly because the curve is increasing, it's curving up. So it's not always the case that right edge values are overestimates. It depends upon the shape of the curve. Okay? We could also do the same calculation with left end values. Okay? There we go. So now when we're looking at each of these four sections, we're going to use the value on the left side. So for the very first rectangle, notice there isn't a rectangle there because we used the left value, which is 0, because the first rectangle goes from 0 to 1/4. So since I'm doing left edge values, I use whatever values on the left, and the height, remember, is I plug the x value into the formula. Well, 0 squared is 0, so there is no rectangle here because the left end value is 0. The second rectangle, I'm going to use the value of 1/4 as the height because it's the left value between 1/4 and 1/2. So 1/4 squared times our width. The third rectangle, I'm going to use 1/2 squared because it's the left value between 1/2 and 3/4. And the last rectangle, I'm going to use 3/4 squared as the height because it's the left value between 3/4 and 1. And again, we can see from the picture here that this is an underestimate. So we know our actual value is somewhere between 0.21 and 0.46875. Okay? So this is a way of estimating the area under a curve by using rectangles. Okay? As we increase the number of rectangles, and we're using n to represent how many rectangles or how many intervals we're going to use over an area or under a curve, notice we get actually closer to the actual area. In the first picture on the left, you see we've used 10 rectangles. It's an overestimate. When we move this number to 30, it's still an overestimate, but it's a much smaller overestimate. We're getting closer and closer to the value. When we go to 50, notice the overestimate is even smaller, and so we can see that we're getting closer and closer to the actual value. So we can say that the area is equal to the sum of the area of the rectangles under a curve as the number of rectangles approaches infinity. And again, this is, remember what we did, it's another similar limit as we started this course. With the derivatives, we went, that distance went to 0. So here we can say the area is equal to limit as n goes to infinity, and n being the number of rectangles, of the sum of all the right edge, the R stands for right edge, not rectangle, the sum of all the right edge rectangles, or the limit as n goes to the infinity of the sum of all the left edge rectangles. So we can do either one. We can do right edge or left edge as the number of rectangles goes to infinity, and these should be equal. Now again, I want to kind of I went through the first example pretty slowly and did it multiple times, but I want to go through this a little bit more generically. Note the width of each rectangle is equal to the interval length divided by the number of rectangles. In the first example, the interval length, since it went from 0 to 1, the interval length was 1. That's the length of the x-axis, or the x values we're looking at, the length of the domain. So in that example, it would have been 1 minus 0, which is 1 up top, and then the number of rectangles you want on the bottom. So we had 1 divided by 4 rectangles, so each rectangle was 1/4. The width of each rectangle was 1/4. Okay? I guess I should have showed that picture so you could see here. So again, the first example, we went from 0 to 1. We wanted 4 rectangles. So the way we find the width of each rectangle is we take the upper x value minus the lower x value divided by the number of rectangles. That's all this means. The interval b minus a, b minus a over the number of rectangles. 1 minus 0 over 1, 2, 3, 4 over 4 divided by 4. Okay? This gives us a more general definition. So we say the area A of the region S that lies under the graph of the continuous function f is the limit of the sums of the approximating rectangles as they go to 0. Okay. Now here, what we've done here is taken, this is kind of expanding. This is giving you each of the rectangles areas. So f of x1, right, that's the height of the rectangle, because we're plugging in the first x value, and then delta x, we've calculated up here, the width of each rectangle is the same. You'll see that in each of these, just as we saw in the first problem. So here we have the height of the second rectangle, height of the third, all the way up to the height of the last one. So this is just kind of expanding that kind of concept. Interestingly, this works similarly for calculating distance given speed over time. Since distance equals speed times time, then the area under that curve actually gives us the distance. I'm not sure if I show you a good diagram of that, a simple one, so you can see it relatively easy. Okay, so see if you can do this problem by reading the values from the given graph. Use 5 rectangles to find a lower estimate and an upper estimate for the area under the given graph of f from x equals 0 to x equals 10. In each case, sketch the rectangles you see. Okay, so we're going to use, go ahead and hit pause, look at this diagram and see if you can do it. Okay, so the first thing is to figure out what is the width of each rectangle. Okay, since we're going from x equals 10 to x equals 0, or really the other way around, but then our whole interval length is 10 minus 0, which is 10, and we want how many triangles or rectangles? 5. So 10 minus 0 is 10, divided by 5, which is the number of rectangles we want, is 2. So we're going to do an upper limit, a lower estimate, and an upper estimate. So we're going to do both left end and right end. Notice that at each interval of 2, we have an exact value here. Actually doesn't, wait, 0, 2, 4 does not have an exact value, so we'll have to estimate a little bit. 6 doesn't either. What am I saying? None of these do. So we're going to have to do a little bit of estimating. So let's see what will happen. So since it's a upper curve, a curve up, the left end will be the lower estimate. Okay. So here we have the left end curve. Every 2, we have, sorry, I lost my train of thought here. So again, since we're using left end values, the height will be here at 0, and this is all just, there's no function here, so we're just using the graph. So we go where it crosses. Where does it touch on the left side for the second rectangle? Here. This looks like a perfect one. Here it's a little bit over, here it's a little bit over, and here it's a little bit over. Okay? So again, you draw your lines, and the height of the rectangle is depending upon whether it's the lower or the left or right values. You go to the left value between 0 and 2. We're going to use the left value, so we go to the curve at 0. From 2 to 4, we go to the curve at 2. From 4 to 6, we go to the curve at 4 for the height. From 6 to 8, we go to the curve at 6, and from 8 to 10, we go to the curve at 8, and then just draw a straight line. Okay. For the upper estimate, we're going to use right-end values, so it's the same function, but now when we do the height, we're going to use the right side value. So for the first rectangle, which goes from 0 to 2, we're going to use the right value 2 and go up to where the curve crosses 2, or the curve crosses 4 for the second rectangle, or where the curve crosses 6 for the third rectangle, or where the curve crosses 8 for the fourth rectangle and 10 for the last rectangle. Now, to figure out the area under these, since we're graphing, we're just literally going to count the boxes 1, 2, 3, 4, 5, 6, etc. through this. And here we're going to have to do some estimating. To me, this looks like about a third. So I have 1/3, 2/3, 3/3, 4/3, maybe 5/3 or 6/3. Maybe altogether they could be about 2. Okay. And so here we get the lower area. If you count all the squares, you get about 40. And if you count all the squares here, again, we've got a bunch of what looks like maybe thirds. So this is 2/3, 4/3, 6/3, you know, anyway. It's some estimate there, but you get the estimates here by just counting the boxes, right? So for example, the first rectangle would be 1, 2, 3, 4, 5, 6. And then we count the second one, 7, 8, 9, 10, 11, 12, 13, 14, etc. So this is just about counting. There's no calculation here. This is a way of looking at it and really understanding about building those